بسم الله الرحمن الرحيم. Welcome to Tahar Scholar. We are ثلاثاء 9 أبريل 2024 or in English Tuesday the 9th April 2024. This is chapter 2 section 2.3 Cramer's method. We have studied in the first lecture the problem and the methods we will study in this chapter, and then in the second lecture we made a revision on matrix algebra, namely the determinants, the identity matrix, the inverse of a matrix, then the null space and the image space, and the rank of a matrix. And today we will focus on Cramer's method. So Cramer, first of all, the history. Gabriel Cramer is a Swiss mathematician between 1704 and 1752. He received his doctorate. He received his doctorate in mathematics, his doctorate at the age of 18. So he was very young at the age of 18. And then he works in the University of Geneva as a co-chair of mathematics in the University of Geneva, University of Genève, until he passed away. He was sick, he has a disease, that's why he died young. And before he died, about 2 years before he died, in 1750, he published a book on algebraic curves. I think in French, Étude analytique des courbes algébriques, if I remember the title. But the topic was on algebraic curves in 1750. In that book, he published the method. So Cramer's method is actually an analytical method, and it is based on determinants. Before to present the method, we need first to introduce a notation. Suppose we have a matrix A in Rm, and we have to solve the system Ax equal B, with X and B belonging to Rm. We need a notation defined like this: A, vector U, I, where U belong also to Rm. And this is a matrix. This is a matrix whose ith column is replaced by the vector U. So we have the first column, A1, the notation I is the column I, the ith column of A. So A1, the first column, then the second column, etc., until the ith column. The ith column is not the column of A, but the vector U. And then we continue till the last column. So this is the definition of this notation. This is the ith column. The ith column. So now we can introduce the theorem due to Cramer, called also Cramer's rule. So theorem, also called Cramer's rule. It's a formula. It's very simple. So if A is invertible, then there, for whatever B in Rm, there exists a unique, the symbol without the mark exclamation is called exist, but with the mark exclamation, it is it means there is a unique something. So there is a unique vector x, unique solution in Rm. Because A is invertible, as we have seen in the last lecture, when A is invertible, the solution is always unique. It exists and is unique, and is given by, and its component, the component of the solution of the vector x, xi, are defined by the determinant of A, the matrix A, all the columns of A except the ith column is replaced by B. As the notation, here instead of U is any vector belonging to Rm. So we have put here the vector B. So B must be at the ith column. For the first component, it's the first column that is replaced by B. For the second column, and so on. The determinant of this matrix over the determinant of the original matrix, determinant of A. Now that's it. And its formula, that's why it is an analytical method. It's an exception. Normally we study here numerical methods, but actually Cramer's method is not a numerical method. It's not an approximation. It doesn't give an approximation. It gives the exact solution and the formula. But unfortunately, because of the determinant is computationally expensive, the method is suitable only for small matrices. Let's see this formula, the application of this formula through examples. We come back to our two systems we have seen in the first lecture and try to solve them using Cramer's method. So, third point, examples. So, first example is our system. Let's write it here. So this is our system, and first thing to do is to calculate the determinants, the determinant of the matrix, and then the auxiliary determinants, one for each component. We have two components, so we will calculate two auxiliary determinants. So the first determinant is of the matrix A. We have already calculated it in the previous section. And we found it equal to, let's write it again, 1, 2.3, we have found it equals to 2.89. Now we calculate let's let's call this delta, and delta 1 by definition is the determinant of A, but the first column must be replaced by B. That is, we leave the first column and the second column is the same as A. But in the first column, we write the vector B, minus 1.5 and 3.9. And for delta 2, by definition, is the determinant of the matrix A, except the second column is replaced by B. So we write the first column from A, but the second column will be replaced by B. It is the same vector here, minus 1.5, 3.9. And we perform the calculation of the determinants as usual. So minus 1.5 times 4.5 minus 3.9 times 0.7. And here 1 times 3.9 minus 1.5 times 2.3. And we find delta 1, I've already done that, minus 9, 4.8, and delta 2 is 7.35. So this is the first thing to do, is to calculate the determinant of the system matrix and then a determinant for each component. And then we apply the Cramer's rule. We apply Cramer's rule. X1 is delta 1 over delta, and X2 is delta 2 over delta. And we replace the determinants by their values. So here we have minus 9.48 over 2.89. And we find minus 3. Here I will use 5 digits after the decimal point. Not like in the first chapter, we used to work only with 3 because of the stability of the algorithm. When we solve either Cramer's or Gaussian elimination, is sensitive to round of errors. Round of errors increase in the algorithm rapidly. So it's better to work with the maximum possible number of digits after the decimal point. But with the hand computing, I will limit it to only 5 decimal points. Of course, with MATLAB, with 16 digits, it is of course more precise. So I find the value to 8, 0 to 8. I rounded the numbers up, only 5. So let's write it, 5 digits after. You will see why it's important later, just now, after that. 5 digits after the decimal point. And we do the same here So we have 735 over 2.89, and we find the value 254,325. Let me check again. Okay. So we have the solution of our system. We can easily check if this is a solution or not by calculating. So let's say here, third point, assess the accuracy. We simply calculate the residual vector AX minus B. If X is the solution, then this should be equal to B, and R should be equal to 0. So R should be the residual. This is called the residual. The residual should be close, not equal, but close, because there is an error, a round of errors when we perform the division and when we calculate also the determinants. Should be close to the vector 0, to 0. And let's do it. R equal the matrix and we find the result minus 0.5, minus 1.9. I have rounded these numbers because we multiply them, we scale them by 10 minus 5. So it is almost equal to 0 to approximately 5 digits. If you count 5 digits, it's almost 0, because we have worked with 5. If you have worked with, for example, 8 digits or 10 digits, we will find here something. Numbers, of course, not 0, but times 10 to the power of minus 8 or minus 10, according to what we have taken as digits after the decimal point. So the number of decimal points you choose when you do hand computing is important. When you work with MATLAB or Octave or any software on computer, generally it uses 16 digits. And the significant digits, you will not have to worry. But with a calculator, in exam, for example, I advise to work with 5 digits to get a better precision. So this is almost equal to 0. You will never find here 0, 0, unless all the numbers are integers, including the determinant, the component, which is seldom, of course. Generally, you will work with floating points, with real numbers. So it's almost equal to 0. But make sure that you find here a small number. If you work with 5 digits, minus 5, minus 4 is okay, but not minus 2 or minus 1. You have made an error. Or plus 2, plus 3, you have, of course, made an error. So it must be close to 0 in the sense or according to what you have what you have used as precision. Precision here is 5 digits after the decimal point. So this is a way to check the accuracy of your result. You calculate the residual and make sure it is close to 0. Let's move to example 2. So here you can also observe that when you have two equations, the method is very simple, very easy, very useful. And often, particularly in first, second year, in the first modules you study in the university, you work in 2 dimensions, 3 dimension, in geometry or mechanics. You work often with in 2 or 3 dimensions. Then Cramer's rule is very useful, very easy to use. So the second example. So this is the second example. We have already seen our goal is to find x. We can write x1, x2, x3, or x, y, z. It's the same. First thing first is the determinant. We have also already calculated it in the previous section, and we find it equals to 48, 52. So it's different from 0, and the matrix is invertible. Then we calculate the auxiliary determinants, one for each component. So let's write first delta 1 here, have space, delta 1. We leave the first column for B, and the rest we copy from the matrix A. So the same second column. And we perform as usual. We can pick any column or any row, and we work. Here, for example, it's better to work with the second column or the third row. So we find the result. I put directly the result because we have already seen how to calculate the determinant of a matrix. To save time, we give the result. You can check, of course, with calculator or with MATLAB. We find 71.49. Then for delta 2, the determinant, so the same matrix A, except the second column, where we put the vector B. So we have here 2.5. So we calculate the determinant as usual. We select any column or any row, and we find the result minus 108.05. And same for delta 3. The determinant of the matrix A except the third column. Third column is and we find equal to minus 105. So now that we have the auxiliary determinants, the second step is the components. x1 or x2 or y, it's okay. So let's write x1 equal delta 1 over delta, according to Cramer's rule. So we have here 71, 49 over 48, 52. And we find the result 1.47341. And we do the same for the other components, for the two other components. So we have our vector x and its three components. Well, the rule is very simple. The hard work is when you calculate the determinants. For 3 components, you have to calculate 4 determinants. The determinant of the matrix, the system matrix, and then the auxiliary determinants. You replace one column by the vector B, by the image vector. For delta 1, the first column, for delta 2, the second column, for delta 3, the third column. So the hard work is in calculating the determinants with a calculator. So it's optional, but it's nice to check the residual. So the residual is the matrix A. And we find the result times 10 to the power minus 5. So it's close. R is close to vector 0 with a precision of 5 digits after the decimal point. This is optional, of course, but it's nice when you have time in the exam, for example, to check your result, or a report, or an exercise, whatever. So you will never find here 0 because of round-off error, but close to 0 according to the digits you have used, number of digits you have used to calculate the determinants and the components of X. So it's very simple, very easy. In 2 steps, the determinants, and then a new fraction or a ratio, the auxiliary determinants over the determinant of the mother matrix. So let us now move to the proof. We have seen the theorem, we have to prove it. Not like in matrix algebra, we have given several theorems without proof because it was a revision. It's not our topic. We need that to understand the rest of the chapter. But here it's in the bulk of the chapter, we have to prove the methods. Any method we use in numerical method, any method, we have to prove why it's true. It's a theorem, why it's true. So proof, that was, I think, the 4th point. We have seen introduction, theorem, examples, now proof. Let us start with the definition of A, B, I that we used in Cramer's rule. We replace the ith column with the vector B. So by definition, the first column of A, the second column of A, till the ith column, we replace it with B. And we continue till the last column of A. So, but AI, what is the column AI? The ith column of A, by definition. But what is AI? It is the matrix A dot EI, where, so this is the ith column, and so what is that? I've seen that before, the standard basis. So EI is a member of the family E, J from 1 till M, which is the standard basis of Rm. We have seen that in the previous section when we revised matrix algebra. So because EI is actually a vector whose elements are all equal to 0, except the ith component is equal to 1. So when you multiply it, when you perform the inner product with A, you get only the ith column of A. All the other will disappear in the inner product. So we get AI. And the second thing, B, the vector B, is the image of X. So using these two facts, we replace them here. And we get AB, the matrix ABI, becomes A with E1, with the first factor of the standard basis. And then A, E2. And then B is AX. And the last column is A dot EM, the last vector in the standard basis. And this is matrix. And remember here, the inner product. So here we have the same matrix A. We have the same matrix A, and we dot it with different vectors. Remember, recall the definition of the dot product of two matrices, A dot B. We have seen that the jth column of C is generated by the jth column of B. Dot the same matrix A. So the matrix A is involved with each column of B, and each column of B will generate the column of C. So this is the jth column of C. The same matrix A, and this is the jth column of B. So the first column of C is generated by the dot product of the first column of B with A, and then the second column with the second column of B with A, and so on. This is exactly what we have, the same pattern. So we have here actually the dot product of two matrices. So recall that and apply it here. So we have A and BI is the dot product of the matrix A with the second matrix. The columns of the second matrix are the standard basis. So E1, E2, except the ith column is the vector X, Now this is the ith column. The ith column, it was B. We have replaced it with AX. Now we have taken A aside, and it becomes X. And we complete the matrix with EM. So this is, again, the ith column. What we call that? What is this? This is the identity matrix, except the ith column. We replaced it with X. So we can use the notation we have introduced in this method. The matrix IM, the identity matrix, except the ith column is replaced by X. So we can write here that ABI is the matrix A dot IM X the vector I. So this is the first step or the first phase in our proof, to find the relation between the matrix A and ABI. And we have introduced the standard basis and then the identity matrix. Because the columns of the identity matrix, as we have seen also before in the previous section, in the last lecture, second lecture of this chapter, that the columns of the identity matrix are the standard basis. But here, all the columns are the standard base except the ith column. So we have used the notation we have introduced earlier. And then we calculate the determinant. We use the distributivity, the determinant, because the determinant of ABI is the numerator in Cramer's rule. So we are calculating it. The determinant of ABI by the distributivity is the determinant of the first matrix times the determinant of the second matrix. This is this one. How to calculate this? Determinant of A is obvious, but how to calculate this? So to do so, let's write this in the expanded form. IM, the identity matrix, except the ith column, is equal, by definition. So the first column is 1, and all the rest is 0. All the rest is 0. And then the second column, the second member is 1, and all the rest is 0. This is E1, and this is E2. So this is E1, and this is E2. And we continue till the ith column, it will be replaced by X, component of X, X1, X2, etc. until Xi. So this is the ith column, and this should be the ith row. And then we continue here Xi till Xm. And we continue till the last column. The last column is 0, 0, etc. Here also 0 at the ith row. All its components are 0 except the last one is 1. Because this is, let's do with another color. This is EM, the last column. Now, how we calculate its determinant? Its determinant, we can choose any column or any row. We choose the column where there are the maximum number of 0, the first column. So we have to calculate the minor to this element only, because the other elements are 0 in the column. So we have 1 with the rest of the matrix, the submatrix, where we have eliminated the first row and the first column. It becomes like this: 1, 0, 0, 0, 0, and then x2, x3 till xm, and 0, 0, etc. till 1. We again choose the first column. I beg your pardon here. Here we have 3 points. This is the ith column. And again, we choose the first column of this submatrix, because all the elements are equal to 0 except the first one. And we continue the process. So we have 1, then times 1, then times 1, then times 1, till I minus 1, just before the ith column. We have calculated the determinant across the columns until the last column before the ith column. So all these columns to get 1i minus 1. And then the submatrix left is the following: xi, xm. So this is the ith column, and the etc. until 0, and the 1. So this is the ith column. What is left in the ith column? We have eliminated x1 in the second, and then we eliminate x3, etc., until we reach the ith row, ith column. So the determinant of this. Here we can choose the row, not the column, because all the terms here are equal to 0 except the first one. So here all the terms of the ith row, all the terms are equal to 0 except the first one. Except the first one. So we have here 1 to the power I minus 1 xi with the minor of xi. We eliminate the row, we eliminate the column, we get, because all the elements on the diagonal here are equal to 1. This is the identity matrix, except the ith column. So here we will get all equal to 1. So we have 1, 0, 0, etc. till 0, and here 1, 0, 1. And on the column you have 1, etc. until 1. This is the identity matrix. This is the identity matrix with m minus I columns times m minus I rows. Because this is I plus 1, we say I plus 1th or I plus first, whatever, I plus 1 column, a row, and this is I plus 1 column. The column that is just after the ith column, because we have eliminated the ith column and the ith row, we get the submatrix that is here. The submatrix is here. It is the identity matrix. The identity matrix. But m minus I times m minus I. A small identity matrix. And its determinant is because this is the determinant, the minor. The minor. So it's the identity matrix whose determinant is equal to 1. Is equal to 1 because it is a diagonal matrix. Its determinant is the product of all the elements on the diagonal, which are all equal to 1 because it's the identity matrix. So we can conclude here, we have still space here. 1 to the power I minus 1 of any power, it's 1. And this is equal to 1, the determinant of the identity matrix. So we have xi. The determinant of im x I is equal to xi. So let's come back and put that here. What was our result? So actually this term is equal to xi. So let's come back here and replace it xi. So we have the determinant of ABI equal to the determinant of A times the determinant of IMXI. And we have just seen that this is actually xi. We have expanded the matrix and calculated it by columns. We found it is equal to xi, which means xi equals the determinant of ABI over the determinant of A. For any matrix in LMM that is invertible. And this is the theorem. Invertible. Determinant of the invertible matrix is different from 0, so we can divide the numerator by the determinant of A. This is the theorem. So we have proven it. Now let's write that like this. So this is it for the first part of Cramer's method. And in the next part, inshallah, we will see a formula for the inverse of a matrix that is deduced based on Cramer's rule, and how to determine the rank of a matrix. But for now, this is it, and see you inshallah next time. Peace.